In our program, Simple Harmonic Motion, you learnt about the oscillations of single systems such as simple pendulum, spring mass system, torsional oscillator, and strip oscillator. Each of these oscillators is characterized by a single frequency and executes simple harmonic motion. But life is not so simple. These systems are idealized in the sense that they rarely exist around us. In nature, the oscillating systems are somewhat complex. To explain this, I have with me models of carbon dioxide, water molecule, and sodium chloride. In carbon dioxide molecule, two oxygen atoms are joined to one carbon atom. Similarly, in water molecule, two hydrogen atoms are joined to one oxygen atom. In sodium chloride, sodium and chlorine atoms are bound together. In organic molecules, the binding is somewhat more complex. In a string, there are a large number of atoms which are joined to one another. These can be modeled in the following way. Here, these identical atoms are joined in an array to one another. Such systems are called coupled systems. You may now like to know what is binding these atoms. The binding or coupling is provided by interatomic forces. We cannot see these forces, but we can model them by constructing a coupled system. Professor Saraf has designed a coupled system by joining two strip oscillators via mechanical coupling, field coupling, and torsional coupling. Let us know about the mechanically coupled system from him.
I have here two oscillators. One is on this side, and this strip loaded at this end, it can oscillate independently. I have another oscillator of similar kind with the same strip and another load. This also can oscillate independently. And at the moment I have arranged them in such a way that their independent time periods are equal. I can make oscillate like this, and you can see that both more or less oscillating with the same time period. Now, I make a system 1 out of it by providing a coupling between the two.
The moment coupler is introduced, oscillators form a coupled system. Will this system behave like independent oscillators? To understand the dynamics of the system, let us disturb one of the oscillators and keep the other one at rest. What do you observe? The second oscillator has started oscillating. But why? This is because it gradually picks up energy from the first oscillator. So we can say that coupling leads to energy transfer. Let us observe this motion for some more time. The first oscillator comes to rest for a moment. At that instant, the second oscillator has maximum amplitude of oscillation. If you continue to observe this motion, you will note that after some time, the amplitude of second oscillator decreases and the first oscillator starts gaining in amplitude. In terms of energy, we can analyze this motion by plotting a graph between the energy of the individual oscillator and time. As the first oscillator begins to oscillate, its energy starts decreasing. But there is a corresponding increase in the energy of the second oscillator till it becomes maximum. At that instant, the energy of the first oscillator is 0. This process continues interchangeably for a long time. So we can say that in a coupled system, energy flows back and forth between individual oscillators and energy transfer is periodic. Now let us concentrate on individual oscillators. Is their motion simple harmonic? The hallmark of simple harmonic motion is a sinusoidal displacement time graph of constant amplitude. But in case of coupled system, the amplitude of oscillations of individual oscillators continuously changes. In particular, when the oscillations of the first oscillator decrease, the amplitude of oscillations of the second oscillator increases. So we can say that the motion of a mechanically coupled system is not simple harmonic. What do you think will happen in case of field coupling? As before, the energy flows back and forth between these oscillators, but their motion is not simple harmonic. You will observe the same behavior in the case of torsional coupling. From these experiments, you may be thinking that the individual oscillators making up the system will never execute simple harmonic motion. But this is not true. From Unit 5 of your course, Oscillations in Waves, you would recall that we can excite modes with definite frequencies. Let us consider in-phase and out-of-phase modes. In in-phase mode, the individual oscillators are displaced equally in the same direction. Let us excite the in-phase mode and observe the dynamics of this system. We observe that the dynamical state of the system does not change with time. The system oscillates with a definite frequency. This means that the motion of the coupled system when individual oscillators are excited in phase is simple harmonic. Such a mode is called normal mode. Let us now excite out of phase mode. In this mode, the individual oscillators are displaced in opposite directions but have the same amplitude. If you observe that as before, the dynamical state of the system remains unchanged. So, this is another normal mode. We may therefore conclude that when a normal mode is excited, individual oscillators execute simple harmonic motion. In no other mode of oscillation, the motion of the coupled system is simple harmonic. A very precise coupled oscillator has been designed by researchers at Center for Development of Physics Education, Rajasthan University, Jaipur. Let us know about it from Dr. Y.K. Vijay.
Here I present you a very precise system of two coupled oscillators. These are two independent oscillators whose time period can be controlled independently. Let us see the construction of one. These are the pivot points, and by adjusting the mass distribution of these two masses, we can control the time period of this oscillator. This is another oscillator where we can control the time period by the mass distribution of these two masses. Now, this is the string where the mass is loaded, which decides the coupling between the two oscillators. The strength of the coupling can be controlled with the mass loaded on the string. We have another arrangement of lamp, the lens, and the screen. Now, this arrangement is used to visualize the motion of the coupled oscillator system as a whole, as well as the motion of the individual components.
Do you see the spot on the screen? It is formed when the light from the lamp is focused by the lens. The strings keep the lens in a vertical position. As individual oscillators oscillate, the lens also oscillates accordingly. As a result, the spot moves on the screen.
When I disturb one of the oscillator, then the spot moves in this line. When the other oscillator is in motion, then the motion is again on a straight line, which is perpendicular to the initial line. When I set both in motion, then it traces out an elliptical path, which is due to superimposition of two motions.
You may now like to know, how would Dr. Vijay excite normal modes and steady coupled oscillations by this apparatus?
If the two oscillators are excited in such a way that they are oscillating in phase, they will continue to do so. We call this as one of the normal mode. Let us see the other situation. Here they are oscillating out of phase. We say this is another normal mode of oscillation of the coupled oscillator.
You may be thinking about energy transfer between individual oscillators in this system.
I disturb one of the oscillator. The motion of the spot is in straight line. Now let us watch for some time. It is gradually tracing an elliptical path. What do we infer from this? That is, the elliptical motion is due to superimposition of the two motions, which means that the other oscillator has picked up some energy and that is also in motion. Now how long it will continue like this, that one of the oscillator transferring energy to the other oscillator because of coupling. Look at the motion of the spot. The ellipse is turning into a straight line, indicating motion of only one pendulum. The first pendulum has come almost at rest and the cycle is repeated. From second oscillator, energy goes back to the first oscillator due to this coupling. Now you can see again it is tracing an elliptical path. When the whole energy will come back to the first oscillator, we expect that the motion will be again on the original straight line. Now you can see the motion is again on an initial straight line when I disturbed the first oscillator and the second oscillator was at rest. So this way we can see the effect of coupling. From one oscillator, energy goes to the other oscillator and comes back to the same oscillator. The other point you can realize is that the size of the ellipse is going on reducing, indicating the total energy of the system is decreasing due to finite damping, because the system is not getting any energy from external source.
I am sure you must have understood the role of coupling when two oscillators are joined together. Let us summarize what you have learned in this program. The motion of individual oscillators in a coupled system is not simple harmonic except when it oscillates with a characteristic frequency of a normal mode. When two oscillators are coupled, we have only two normal modes. For a system of two coupled oscillators, energy flows back and forth between them. But a continuous medium, like the string of a musical instrument or our atmosphere, consists of a very large number of atoms. Such a system will have infinite normal modes of vibration, and energy transfer due to coupling leads to wave propagation. Wave propagation finds great use in medical diagnostics, oil exploration, and weather prediction. It is also responsible for seeing and hearing. It involves a lot of good physics, which you will study in block 2 of your course oscillations and waves.